Hey folks, my name is Nathan Johnson. Welcome to lecture 12 of vector calculus, which is all about gradient fields. Okay, so the idea today is we're going to be looking at the special subclass of vector fields that arise as the gradient of a scalar field. And we looked at one particular example of this last video, but we're going to really dive into it a little bit deeper today and talk about, how can you tell, for example, whether or not a vector field is a gradient field? Okay, so let's just start off with the definition so that we're all on the same page. Suppose that you're working in n-dimensional space, and in particular in some domain in n-dimensional space. It doesn't have to be all of n-dimensional space. Then what a gradient field is it's a vector field with the special property that there's some scalar field out there for which the vector field is the gradient of that scalar field. In other words, if you take any scalar field and compute the gradient of it, yes, that's a gradient field, okay? That's, we talked about last video about how it's a vector field, and we're just calling those types of vector fields gradient fields, okay? And the scalar field that gives rise to it, we call a potential function of the vector field, of the gradient field, okay? And so what we're going to be doing today is we're going to be talking about, okay, I've got some vector field sitting in front of me. How do I tell if it's a gradient field in the first place? Like, how do I tell whether or not there is this scalar field in the background? And furthermore, like, how do I find it if there is this scalar field in the background, if there is this potential function that gives rise to it? Okay, and then later on, what we're going to see as we go on in the course is if the vector field that we're working with happens to be a gradient field, so many things work out so much nicer, okay? They're kind of the best vector fields that we could ever hope to work with, okay? But we'll get to that as we get there. That's not going to be this video. Okay, so let's talk about terminology just a little bit before we get going. And the one thing I want to point out is that if you are a physics student, then the terminology you see in your courses might be a little bit different. Okay, so the way that we've defined things here and the way that most math textbooks define things is we say that the potential function of the gradient field is this thing that we're calling little f. It's the function whose gradient is the gradient field. Okay, whereas in physics, usually negative little f is called the potential function because then it sort of represents potential energy or something like that in a more natural way. For us, we're not going to include the minus sign just because it's a little bit mathematically cleaner not to include it. Okay, we are still going to use terminology like this though. Okay, so this terminology, which again we're sort of borrowing from physics, if we say equipotential line, like what that means is just a contour line. Because if you think about that, like equipotential, what should that mean? It means the potential function is constant, it's equal everywhere on that line, which just like that's what a contour line, right, is, right? Like it's a line or a curve where that scalar field outputs constant values, outputs, the same value everywhere on that line. So an equipotential line, that's just another name for contour line. Or if you're in higher dimensions, right, if you're in 3 dimensions or larger, it's not a line or a curve anymore. Now it's a surface, so we call it an equipotential surface. Okay, so anyway, let's return to this question that I said we're going to deal with. How do you tell if a vector field is a gradient field or not? Okay, and sort of the key insight is that if it were a gradient field, well, then, okay, what would that mean? If this were a gradient field, this particular vector field right here, okay, so f of x, y, z equals x z squared plus 2yx, x squared plus y minus z, and then 2xyz. If that were a gradient field, then what that would mean is there's some scalar valued function out there that when I compute its gradient, I get this thing. In other words, the first entry would have to be the x partial derivative of that scalar field, okay? So if there were a scalar field for which this is a gradient, then the x partial derivative of it would have to equal this first entry. Okay, and the y partial derivative of it would have to equal that second entry, just because that's how the gradient works. It's the x partial, then the y partial, then the z partial. So similarly, the z partial of the scalar function, that would have to be 2 times x times y times z. Okay, now though, if that were true, what would happen when you go one step farther? What happens when you compute mixed second partial derivatives? And remember, there's a theorem for multivariable calculus that tells you, like, as long as your mixed second partial derivatives are continuous, so like as long as your function is nice enough, then they're equal to each other in the sense that, like, you don't have to remember the order. For example, like if you do the x then the y partial, you're going to get the same thing as the y then the x partial. Okay, so what we can do is, well, we can just take these first partial derivatives and compute the second derivative from them. And if this scalar field actually did exist, what would happen is, for example, when I take the y partial of this one on the left to the y partial of the x partial, I would have to get the same thing as when I compute the x partial of this thing, the x partial of the y partial. Okay, but some of those equalities actually break down, okay? It turns out that's not true, okay? It actually is true for this very first one, for the y of the x and the x of the y. In both cases, you're just going to get 2x, okay? If I do the y partial of this, I get 2x. If I do the x partial of this, I get 2x. Yay! That's not enough. You need all the mixed second partials to equal each other if this scalar field actually exists, okay? And for this particular vector field, if we do this sort of thing, comparing all pairs of subscripts, pairs of variables that we can take derivatives with respect to, well, if we do the zy and yz pair, again, like if the scalar field existed, those would have to equal each other. The mixed yz and the mixed zy partial derivatives would have to equal each other, but they don't, right? If I take this first y derivative and compute its z derivative, I just get -1. And if I take this z partial derivative and compute its y derivative, then I'm going to get 2xz. Okay, and that's not the same. 2xz is not equal to 1. Okay, so because some of the mixed partials don't match up how they would have to, we could conclude that, no, like this scalar field, this hypothetical potential function, just doesn't exist. None work. So this vector field, our conclusion is no, it is not a gradient field. It's a fine and dandy vector field, but it's not this special type of vector field that we're calling a gradient field. Okay, let's do another example. Okay, so again, it's going to be a vector field from R3 to R3. This time it's defined by fx, y, z equals 2x plus 2y, 2x minus 3z squared minus 6yz. And same question, is this a gradient field? It's a fine and dandy vector field, but is it a gradient field? And we're going to do the same thing. We're going to say, okay, first entry, if it were a gradient field, then this must be the x partial derivative of the potential function, and then this second entry must be the y partial derivative of the potential function, and this third entry must be the z partial derivative of the potential function, if a potential function existed. Okay, and let's just check the mixed partial derivatives, the mixed second partial derivatives, just like last time. Okay, so we compute the y derivative of the x derivative and the x derivative of the y derivative. And I mean, in this case, like if we do the y derivative of this, we get 2. If we do the x derivative of this, we also get 2. So yay! The mixed xy second partials, those agree with each other. What about the mixed xz partial derivatives? So we do the z derivative of the first one and the x derivative of the last one, and for both of those we get 0. Yay, those match. The mixed xz partial derivatives match. Okay, what about the mixed yz partial derivatives? So we do the z derivative of this and the the y derivative of this. So z and then y, okay? And in both of those cases, we're just going to get -6z. So those match. And then those are all possible pairs of variables that we can take derivatives with respect to. So all of the mixed second partial derivatives agree with each other in the way that they would have to. And it turns out that's enough, okay? So there's a nice theorem that says, okay, again, like subject to some sort of conditions on the domain and on the function that you're working with, subject to those nice conditions, yeah, like as long as these mixed second partial derivatives match, then yes, there is a potential function in the background. This is a gradient field. And we'll get to that theorem later in the course when we have a bit more machinery. But for now, like once we've done this check, maybe we're not convinced. Maybe we're thinking, okay, like even though this passed, like how do I really know it's a gradient field? Well, fortunately, you can find the potential function, and the way you find it is just by integrating, okay? So what I'm going to do is I'm going to say, okay, this is the x partial derivative of my potential function. So what I'm going to do is I'm just going to integrate it with respect to x. And what happens when I do that? Okay, well, the 2x becomes an x squared. 2y is a constant as far as x is concerned, so it just becomes 2xy. Okay, and then I have to add on a constant as well, right? If I'm doing an indefinite integral, I've got to add on a constant, and that's what this g of yz over here is, okay? That's a constant as far as x is concerned, right? I'm not just going to add a plus c here because like it's a constant as far as x is concerned. It's allowed to depend on y and z. If I just say like plus c over here, then I'm being too restrictive, okay? It's allowed to depend on y and z. Okay, so my potential function, if it exists, had better look something like this. Okay, but this is what I get when I work with the first entry. There's no reason I have to work just with the first entry. Let's work with the second entry as well. The second entry, right? Remember, that's the y partial derivative of my potential function. So how about I just integrate that with respect to y, right? This is just the second entry in my vector field. Okay, if I integrate that with respect to y, 2x, that's a constant, becomes 2xy. negative 3z squared, that's a constant as far as y is concerned, so it just becomes negative 3yz squared, and then plus a constant as far as y is concerned. My plus constant in this indefinite integral is something that depends on x and z this time, okay? And it's maybe a different constant function than in the previous example, so I just give it a different letter, calling it h instead of g. And then we do this one more time. I'm going to do it for the final entry as well. That's the z partial derivative of some potential function. I'm just going to integrate with respect to z. Okay, and what happens then is this z becomes a z squared over 2, so I get negative 3yz squared. And then again, plus some constant function, constant as far as z is concerned, so it's allowed to depend on x and y. And again, it's just a different constant function than in the previous two lines. Okay, and now here's the trick. Okay, what I've got to do is I've got to find a potential function. I've got to find a scalar field f that is of all three of these forms, right? I want to find a function f, a scalar field that equals this top thing and equals this middle thing and equals this bottom thing for suitable choices of g, h, and l, so that when I do the partial derivatives of it, yeah, I get these things over here. Okay, and here's the, I mean, you just start, trying to eyeball and trying to put terms together, okay? My scalar field, it should have an x squared term in it. It should have a 2xy term in it. It should have a negative 3y squared term in it. Let's maybe just leave it at that, okay? I guess that my scalar field, my potential function, maybe could just be exactly what I said. Maybe it's just x squared plus 2xy minus 3yz. And once you have a guess from looking at these three lines up here, just take partial derivatives and verify that they work, right? If I do the x partial derivative of this, I get 2x plus 2y, and this term goes away. So I just get x squared plus 2y. Oh, that's this thing over here. Yay, my x partial derivative is correct. If I do the y partial derivative, this first term goes away. I get a 2x here, and I get a negative 3z squared. Oh yeah, 2x minus 3z squared. Yay, my y partial is correct. If I do the z partial, I just get a negative 6yz. That's the correct thing as well. Okay, so it has the correct partial derivatives. If you like, you can think of this as like, what do we choose my g of yz to be? Well, I chose it to be negative 3yz squared. What did I choose my h of xz to be? Well, I chose it just to be x squared. And what did I choose my L of xy to be? Well, these first two terms, x squared plus 2xy. And once I make those choices for g, h, and L, then all three of these lines equal each other, and that's my potential function f. Okay, and it turns out this procedure will always work for you, okay? As long as the mixed second partial derivatives up here match with each other, then you can always do this integration stuff to find your scalar field, your potential function that's hiding in the background. Okay, and that'll do it for today. Thanks for watching, everyone. I'll see you in another couple days when we talk about flow lines.